Welcome to our lecture online, and here's our third video on motion in one dimension. Here we're going to learn how to graph position versus time. So how to graph the position of something that's moving and changing velocity and accelerating over time. So let's say we have our example here that says a subway train accelerates at 0.5 meters per second square, I should say, for the first 60 seconds, assuming the train starts at rest, then maintains that velocity for 240 seconds, which is 4 minutes, and then it slows down for 30 seconds at -1 meters per second squared. What would the position as a function of time look like as the train goes from one station to the next station? All right, so first, for the first 60 seconds, it is accelerating, so the position will look parabolic. So it starts out like this, and notice that the slope of that line is increasing. Because remember, the slope of an x versus time graph should be velocity, and as it's speeding up, the velocity should be greater and greater and greater, so the slope should be greater and greater and greater. So you have this parabolic curve. Also remember that the equation of kinematics for position, x is equal to x sub naught plus v sub naught times time plus 1/2 at squared. Now in this particular case, it started from the first station, position is 0, so this could be 0. And it started at rest, so the initial velocity is 0 as well. And so we can say that x equals 1/2 acceleration times time squared. So as time goes by and it's accelerating, x will be increasing at a quadratic rate. That's why the slope looks like a parabola. But then we get to this point right here. So at this point, 60 seconds have elapsed, and the train will have reached a distance which we don't know yet. So let's call this x1, the first distance after it stops accelerating. We'll figure out in a moment how far that is. Then, and I have to be careful here because I'm going to run out of room, so I'm going to have to change this just a little bit so that I can actually get this on the graph. So let me change this again, like that. So we start out, and it's still a parabolic curve, but we don't want to make it too steep initially. So there we go. So there's our first position, x1, after 60 seconds. Now after the first 60 seconds, it now maintains the speed that it obtained, which means that it's going to continue like this in a straight line until another 240 seconds are elapsed. Does this kind of look like a straight line? I was hoping it would. There we go. So there's a straight line. So that's an additional 240 seconds elapsed. The train will now have reached this position right here, and let's call this x2. And what does the train do now? Well, for the next 30 seconds, it slows down back to 0 meters per second, and it will then have reached its next station. So then that would be a negative acceleration, so the velocity will be slowing down, so it will kind of look like this. And so after 330 seconds, it will then have reached its maximum displacement, x sub 3. Let me put this over here, x. Okay, now, that's what the graph looks like. It's a parabolic increase, then it's a constant velocity, and then it's a parabolic decrease in velocity. So that's a position versus time graph for an object that starts from rest, begins to accelerate, reaches maximum speed, maintains that speed, and then slows down like that. In an x versus t graph, we have the slope of the graph and we have the area underneath the curve. Now the slope of the graph, the slope of that graph, is equal to the change of position versus time, and of course that by definition is velocity. So that means in an x versus t graph, in a position versus time graph, the slope is equivalent to the velocity of the object. The area underneath the curve, that has no meaning at all. No meaning. So there's no physical meaning to the area underneath the curve. So we can just ignore that. Meaningless. We still want to find x1, x2, and x3. Do you think we can use that equation right there to find x1, x2, and x3? I bet we can. So to find x1, that is equal to the initial position and initial velocity, which is 0 and 0. So it would be 0 plus 0 plus 1/2 times acceleration. The acceleration was 0.5 meters per second, so 0.5 meters per second square, I should say, times the time elapsed. 60 seconds elapsed, 60 seconds, and we have to square that. So 60 seconds squared, that's 3,600. divide by half, and divide by half. So that would be 900. So in the first 60 seconds, the train reached a distance of 900 meters. All right. Now, can we figure out how far the train traveled in the next 240 seconds? Well, in the next 240 seconds, the velocity was not changing. That's why this is a straight line, as straight as I could draw it. And so, can we use the equation of kinematics? Yes, we can. Because in that case, we can simply go to the equation of kinematics. We'll rewrite it. So we have x sub 2 is equal to x sub naught. Of course, x sub naught was the 900 meters, wasn't it? Plus v sub naught times time. So now for the second segment of this motion, it did have initial velocity. It was moving at some initial velocity. We have to figure out what that is. And then we say plus 1/2 at squared. And of course, there's no acceleration at that time because the train is not speeding up anymore. So how do we find the velocity of that point right here in its position? Well, for that we use the other equation, kinematics, where we can write that v is equal to v sub naught plus at. So for the first segment right here, we can say that the initial velocity was 0. The acceleration was not 1, but 1/2 meter per second squared. And it did that for 60 seconds, which means that in the first segment of its motion, it actually sped up from 0 to 30 meters per second, which becomes the initial velocity of the second segment of its motion, which is going to go in here. So we can say that x sub 2 is equal to 900 meters, because that's how far it traveled in the first segment, plus 30 meters per second times 240 seconds. So in that second segment, it traveled 30 times that would give me 7,200 meters. So from there to there, it traveled 7,200 meters. Add 900 meters to that would be 8,100 meters. X sub 2 is equal to 8,100 meters. All right. Now, how far did the train travel in its third segment in this time frame, the last 30 seconds when the train comes back to a stop? Well, for that, again, we can use equation of kinematics. We can say that x sub 3 is equal to x sub, well, instead of initial, I can probably call it x sub 2, right? That was the position at the end of the second segment, x sub 2 plus v sub 2 times t plus 1/2 at squared. So I'm going a little unorthodox here. Instead of writing sub naught, I can simply say that's the velocity at the end of the second segment. So x2, at that point, I had already traveled 8,100 meters. I need a plus here. V sub 2, that was the velocity at the end here. Well, that was 30 meters per second. The time here in this equation only relates to this segment right here, the 30 seconds in that segment. So it would be 30 meters per second times 30 seconds plus 1/2 times acceleration, which is a negative 1 meter per second square, so negative 1 times the 30 seconds squared. The time in my third segment is only 30 seconds long, so I have to take 30 seconds. Just as I used 240 seconds in my second segment, I should use 30 seconds in my third segment. All right, so this is equal to 8,100. That's how far it traveled by the time it gets to the third segment, plus 900. That's how much farther it would travel. It wasn't slowing down, but since it's slowing down right here, I have to subtract 30 squared times 1/2 times a minus. That would be 450. So in the end, the total distance traveled would be 8,550, and that's what x sub 3 is equal to, 8,550 meters. And so, in short, we first graph the motion. We have an acceleration, constant speed, and a deceleration. That is what a graph looks like for an object that starts from rest, accelerates, holds its speed, then decelerates back down to 0, which is an x versus t graph of such an object. Then to find out how far the object traveled in each of these three segments of its motion, the acceleration segment, the constant velocity segment, and the deceleration segment, I use the equations of motion right here, right there, and right there in order to find the distance traveled in each of those segments, add them all up, and we can identify how far the train traveled by the time it reaches the next station.